In week 4, Dr. Bosma taught us all about ions. Sodium ions have a positive charge. They are attracted to the inside of the cell, which is negatively charged as a result of large static proteins. This creates an electrostatic force pushing the ions in. There is a greater concentration of sodium ions outside of the cell membrane. This creates a diffusion force pushing inwards in the direction of low concentration. Because of the electrostatic and diffusion forces, sodium ions really want to enter the cell. Potassium ions are also positively charged. Just like sodium, this creates an electrostatic force pushing the ions in. But unlike sodium, there is a higher concentration of potassium ions inside the cell. This creates a diffusion force pushing out of the cell, resulting in opposing forces instead of converging forces like sodium. Since the electrical and diffusion forces are opposite, potassium wants to leave the cell, but only weakly. If the ions had it their way, they would distribute across the membrane, moving with their concentration gradient. But this distribution doesn't allow for the eventual generation of an action potential. Instead, we need an electrochemical gradient with sodium ions on the outside and potassium ions on the inside. The mechanism responsible for maintaining this ion distribution against their concentration gradients is a funky little protein known as the sodium-potassium pump. The protein pump is a form of active transport. It uses energy in the form of ATP to move sodium and potassium ions against where they want to go. Let's take a look back at our cell membrane. 3 sodium ions and an ATP molecule bind to the protein. Adenosine triphosphate degrades into adenosine diphosphate, releasing energy and leaving a phosphate molecule bound. This energy release changes the protein's conformation. Sodium ions are moved across the membrane and released outside. Sodium ions diffuse away from the protein while 2 potassium ions bind. The phosphate molecule is now released, allowing another conformation change. 2 potassium ions are moved across the membrane and released inside. The pump is now back to its original shape and ready for an ATP molecule and 3 sodium ions to bind. The sodium-potassium pump transports 3 sodium ions out of the cell and 2 potassium ions into the cell against their concentration gradients. This is an essential mechanism for neural communication because it sets up the cell for resting membrane potential.